Hello, everyone. I'm Eric Hyam, Technical Editor with Microwave Journal, and I'd like to welcome you to the next installment of our Technical Education webinar series. This webinar is entitled Innovation in Satellite Communications and Emerging ESA Technologies, and it's sponsored by RFMW and Qorvo. Today's presentation will be given to us by Paul Prudhomme from the High Performance Solutions Group at Qorvo. This webinar will explore the latest advancements in satellite communications with a focus on the engineering challenges and innovations driving LEO, MEO, and GEO orbits. Paul will delve into the architectural differences between these satellite systems, market trends, and the growing role of electronically scanned arrays, ESAs, in multi-orbit high-throughput applications. The webinar will cover market trends and growth opportunities, particularly in LEO constellations, technical product examples from Qorvo's SATCOM portfolio, including parabolic antennas, phased array terminals, and high-power amplifiers, differentiation strategies that improve system efficiency, reliability, and data rates. The webinar will provide insights into the forefront of SATCOM design, product differentiation, and system-level performance. But before we begin, let me cover a few logistics. If you'd like to download the presentation slides for reference, you'll find a copy in the handouts window. We'll have time for questions after the presentation. To ask one, please type it into the Q&A window at any time. The presentation is being recorded, so it'll be available to watch again and recommend to your colleagues. Now let me introduce our speaker. As Senior Product Line Manager, Paul is responsible for Qorvo's GaN MMIC power amplifiers. With 30 years of industry experience in customer-facing marketing and product development, his primary focus is wireless systems from circuit-level design to full system architecture. Paul earned a BSEE in Communication Systems and a EE from Northeastern University and an MBA from Southern Methodist University, Cox School of Business. And with that, let me turn things over to Paul.
Okay, thank you. Hello and welcome everyone. We're going to dive into a presentation on a topic that I like quite a lot, particular communications, particular SATCOM communications today. During my engineering career, I spent a lot of time on the bench. So parts, circuit level stuff, board level stuff, building systems, did system architecture and comm systems. So it's a subject that I like a whole lot. And so today we'll just kind of dive into the overall agenda. And so, we'll just start off briefly talking about satellite orbits as a review. We'll cover three. There are a few more, but LEO, MEO, and GEO. And then talk a bit about market trends in the SATCOM space. And then we'll weave into that, some product tables from some of the Qorvo product offerings and really how they map into, the SATCOM space, but also how we're designing products today, with the changes that are taking place. In particular, this thirst for higher data rates. So high throughput systems, require a different approach in how amplifiers are designed today. And that's been incorporated, here at Qorvo on the PA and LNA side for probably 3+ years. And we'll dive into that a little bit more. From there, got a little sampling of customer products to kind of map, the different type of end devices that are designed and that active semiconductors get designed into, and just to try and make that concrete for the audience. And from there, we'll talk a little about the SATCOM beamformer circuits. And that particular architecture is interesting because we're going to contrast that to the parabolic reflector antenna with the typically a single transceiver, or it could be dual transceiver, but it's kind of an interesting comparison when you look at both architectures and how they apply to where things are playing in the world today in the comm space. We'll also talk about a couple of bands of new power amplifiers. And I'll point out, some of the specific things we've done from a design standpoint that make them attractive for SATCOM uplink and SATCOM downlink. Go through a few technical examples and wrap up, and we'll go into a Q&A session. This is a neat image that shows, 3 of the orbits. I'm sure the audience might be familiar with a few more, but just to kind of illustrate the point, the GEO satellite is, way out there in space, such that it's effectively, stationary over a point on Earth, and it just kind of rotates at the same rate as the Earth's rotation. So it's effectively, a fixed point in space that the terminal, the ground terminal or the air terminal, can then point to. And so what makes GEO kind of interesting in that sense is that the satellite's fixed, and then the terminal can be stationary or moving. So a familiar example of that would be a VSAT terminal on top of a business. You see them on gas stations often, or some smaller businesses where they may be outside of telecom and fiber connections. We also see them. You take direct TV or Hughes satellite TV, so television services where you've got parabolic fixed antenna sitting on the roof pointing to a GEO satellite. So satellites fixed, and then the stationary or moving. But as we look at the middle Earth orbit and the low Earth orbit satellites, you've got satellites that are moving at a much faster speed. Like GEO's not moving, but a LEO's going from horizon to horizon in about 15 minutes. And then the amount of time that it's in viewing space could be something like 3 to 8 minutes, depending on where you are. So if you're in a mountainous region, that look time is going to be far shorter. So now you've got a satellite that's moving pretty rapidly across the sky, and then to have service to it, that satellite has to be tracked by the ground terminal. And so that's done, with electronically steered arrays, but it's also done with mechanically steered antennas. So that's how service is maintained as a satellite's moving across the sky. So LEO is the fastest thing moving across the sky. And then the middle Earth orbit, something like GPS, has about a 12-hour period. So moving across the sky, but not as challenging a tracking operation as it would be for a LEO satellite. And in all cases now, this terminal can be stationary or the terminal can be moving. So that's a good overview of the satellites and also the challenges that the terminals do face. In terms of satellite market trends, overall it is a growth trend. So for those building terminals or in the SATCOM business, seeing a growing market is a nice place to be. And one of the key trends here is the need for higher data bandwidth. So that's just been a general trend that's going on, since the 90s, right? More bits per second, through the pipe, whatever the pipe may be. And with the LEO satellites now, we've got constellations from different operators that range from hundreds of satellites to thousands of satellites. With the growth plans of more operators entering into having satellite constellations consisting of thousands of satellites, it is a growth area for terminals as well as the satellites themselves. One of the interesting things about LEOs is the service time, or the amount of the service life of the satellite can be 2 to 3 years. In some cases, we're seeing that extend longer. But you just imagine you've got 100 satellite constellation or a multi-thousand satellite constellation, and the service life is, say, 3 years. So you got a 3-year cycle where satellites are dropping out, then other satellites have to come up and replace those to maintain overall service coverage. It is quite a different model for the life cycle of a satellite in contrast to GEO, where GEOs are designed for really high reliability because the expected service life is 10 to 15 years. So quite a contrast between these two satellite orbits and the considerations that go into the design and the life cycle of each. What makes LEO kind of interesting is with this shorter service life, they tend to use commercial off-the-shelf components, which satellite manufacturers do some upscreening to, but has nowhere near the expected high reliability life of devices that are going into a GEO terminal. Another trend is phased arrays are employed. And especially on satellite, the upper image to the right, you see the size of those arrays. These arrays are then sub-partitioned to provide service to hundreds of users simultaneously. So you've got large arrays that are sub-partitioned down that provide directed beams to the individual terminals. So quite a complex high-tech setup for the satellites in LEO orbit. And then the comparison and the size of the installed base. GEO installed base is roughly 400 satellites. The lower right image on this slide, this is the first GEO satellite that went into orbit in 1965, and it's pretty interesting photo from way back. And even take note of the size of the satellite. I think what I read about is I think it weighs something like 70 pounds, right? That's pretty amazing. But so GEO launched into orbit in 1965. And today we've got thousands of LEOs that are going up with, say 3-year service life. Quite interesting dynamics. So on the terminal side, one of the key market trends here is electronically scanned arrays or electronically steered beams on these satellite terminals. And so what happens with this relatively quick period of time where the LEO is in service over the terminal, if it's 8 minutes or 3 minutes, one of the key requirements here to maintain service is a fast switching time. So the benefits of an electronically steered array become kind of obvious in comparison to a mechanically steered reflector. The electrical being really quick in terms of hundreds of nanoseconds to under 10 microseconds, you go from satellite to satellite quite quickly without an interruption in service. Whereas for a mechanically steered antenna going from here, gotta go to there, it's going to take more time to continue service relative to the electronically steered array. So that makes the electronically steered arrays quite attractive for the LEO space, and also attractive when you've got mobile ground terminals or airborne terminals, say for in-service connectivity on a commercial flight. So with electronically steered arrays, you can support LEO, MEO, and GEO with a single antenna solution. And then from a growth standpoint, the terminal. The quantity of terminals, the growth rate of that is pretty impressive. So in the year 2020, there was about 500,000 terminals in the market, and that's projected to grow to 1.5 million in 2028. There's other projections that have that number considerably higher. So that's it's attractive to folks making terminals and those supplying electronics that go into the terminals. So it just looks at growth for a global market that is quite interesting in business. A couple of ideas with parabolic reflectors. In comparison to the electronic arrays, it is a lower growth rate, but the architecture itself still remains relevant. In particular, the parabolic reflectors are pretty inexpensive, right, compared to a phased array that has a bunch of electronics. So you've got beamformers on each antenna. What makes a parabolic reflector kind of interesting is relatively inexpensive antenna, relatively inexpensive transceiver, at the lower power levels, 10, 20, 50 watts. But you've got quite a high gain antenna and a narrow beam width. So quite attractive for especially for the GEO orbit. That's quite an attractive architecture. And then for ground stations, gateway type terminals, large high gain antennas is what we typically see at satellite comm centers. In terms of overall bands of operation in the SATCOM space, this is a mapping of frequency bands to recommended power amplifiers, low noise amplifiers, and beamformer integrated circuits. We presently have standard products for these frequency ranges and some custom products for some of the other satellite operating bands. So at C-band, we've got a few products in the portfolio. May or may not expand that market. At X-band, we've got a new product in the market, and now we've got a number of additional on the roadmap that we'll be taking forward. The interesting markets are Ku band and Ka band, where it's robust for PAs, LNAs, as well as beamformer ICs. So a lot of activity, across the globe for Ku and Ka band components. And we also listing the beamformer ICs. So over to the right of this chart, we're making reference to RxTX beamformer ICs for both Ku band and Ka band. A few years back, we introduced the QV band SATCOM downlink amplifiers, and our roadmap includes uplink amplifiers for 46 gigahertz as well as 48 gigahertz. And then W band, E band is something that customers have expressed interest in. So we're going to expect to have products WE band maybe 18-24 months, and for the Q band, V band uplink, that's about 18 months into the future. But this chart itself is just, it's a recommended product chart. It's a quick reference and look up to kind of map frequency bands, frequency ranges, and some recommended products should there be a need there. In this slide, we're providing a sampling of SATCOM equipment to really illustrate the different form factors. And along the top row, the satellite image indicates phased arrays. We see like 4 large phased arrays there, and then upper left, upper right, and bottom middle of that LEO satellite image. We've got reflector antennas for different type of transceiver. In the center for uplink transmission, there are many manufacturers in the world who very good at solid state power amplifiers as well as block up converters. And those are offered in many frequency bands as well as power levels. And so for Qorvo, we make the engines, whether it's packaged or die in the form of MMIC power amplifiers and low noise amplifiers that the SSPA manufacturers in the world. And, if they select, they design those into, these high power amplifiers for gateway type terminals. And top right, example of a parabolic reflector type of a VSAT terminal, as well as used for television services. And still an interesting type of architecture. You see them used in man packs for military type applications, as well as for even electronic news gathering. It tends to have parabolic type high gain antennas. And then along the bottom row is where really the newer technology is on display. So this is a sampling of phased array terminals. The left and center image terminals are implemented with silicon beamformer integrated circuits at relatively low transmit power levels per antenna element. And then there are many power amplifiers to drive many antennas. So overall, the EIRP that needs to be achieved to establish the link is done by scaling the number of antennas that make up the phased array terminal transceiver. And then the terminal on the right, this is a different approach architecturally. It's a phased array, but it's using a metamaterial type of technology. And the way that's achieved is higher power instead of low power 20 milliwatt type transmitters. The example over on the lower right, 25, 50 watt type PA that then gets divided down among all the radiating elements that make up that type of terminal. So that's metamaterial on the lower right, and then lower center, lower left is silicon beamformer type technology. And all three are electronically steered arrays. So next we have a sampling of Ku band SATCOM beamformer ICs. and one for receive side, one for transmit side. And in each of these are quads. So there's a 4-channel transmitter, dual polarization on the TX side, then 4-channel dual polarization on the receive side. And the slide lists some of the attributes of this, and operates off of a 1.2 volt power supply. And one of the key features is the zero cal capability, which really simplifies the array calibration step. So it actually eliminates the array calibration step, but quite valuable for large phased array in the manufacturing environment. And then over on the next, this is a KKA band. And again, each of these, one 4-channel for transmit, one 4-channel for receive. And so 4-channel dual polarization for each of these. And again, 1.0 polarization, silicon CMOS. In terms of power amplifiers, one of the things we go through when we're looking at the existing portfolio and looking to expand with a new amplifier design, this is kind of a typical process that we think through as we're defining a new device. And one is customer feedback, right? What's going on in the market? What's our existing portfolio? What's the customer asking for? What is the competition doing? And so, with Qorvo across, a number of these bands, we have an existing portfolio of amplifiers. So we've got, that type of in-house knowledge, but we're looking at, what else needs to be done to continue innovating to bring, higher performance with the newer devices to remain, very competitive and to win market share. And so, taking those inputs into consideration, we start off with, okay, how are we going to size the amplifier, right? And, for SATCOM as well as other type of linear communications, it really is how much linear power is needed for the application, or how much linear power is needed for the MMIC PA that we're seeking to design. And so what we want to do there is, right size the amplifier such that, for something like GaN, we don't want to make something that's too big and you get a bunch of GaN die area that's driving cost. So we want to get that right balance of linear power and saturated power for the application, which, traditionally for SATCOM, you could say it was relatively easy with offset QPSK type modulation, where the overall linearity requirements were not terribly stringent. But now we're in a time where high throughput is the growing requirement. And high throughput, how's that achieved? Well, it's achieved with higher orders of modulation is one of the methods of achieving higher throughput. And so with higher orders of modulation, you move from offset QPSK to something like 16 QAM, 64 QAM, or more complex. So more bits per second in the same bandwidth, that requires a different linear power metric, because now the average power is backed off further from saturation. But you need to have a very good AM to AM distortion characteristics, as well as very good AM to PM distortion characteristics to minimize error vector magnitude, which is a metric of signal to noise ratio for higher order modulation schemes. So linear power is really the first key consideration that we look at. And then from there, we kind of rank PAE as second, so efficiency at linear power is another key consideration. We kind of rank it as maybe a number 2 in terms of how we're defining an amplifier. But why is efficiency? Well, it's the amount of heat that's generated, the amount of heat that needs to be managed, and the overall PA. And so that affects reliability, and it results in lower junction temperature, all else being equal. And from there, also related to linear power and an enabler for high data throughput systems is the concept of instantaneous bandwidth or video bandwidth. And so we've been designing amplifiers for a good 3-4 years now, and we're defining the instantaneous bandwidth typically to be the same as your overall operating bandwidth for the amplifier. That's not always the case, but it's typically the case. So for something like for KU band, that's 13.75 to 14.5 gigahertz. That's now that's relatively easy, being it's 750 megahertz of overall bandwidth. But we want that amplifier that's operating that band to have consistent distortion performance across that entire 750 megahertz of bandwidth. When we move up to Ka band, where we're 27.5 to 31 gigahertz, that's quite a wider span of frequency to have constant distortion performance across the bandwidth. But that's still the objective, in amplifier design. And so the idea is whether a customer is operating, a narrow band 30 megahertz, has a 30 megahertz channel, or is filling out the entire spectrum with carriers at 30 megahertz, or is doing something like, let's say, 4 carriers at 500 megahertz occupied bandwidth per carrier. The point is the distortion performance needs to be constant across that entire bandwidth to enable a near constant signal noise ratio that enables high throughput performance for a SATCOM amplifier. And then from there, we look at package size, weight, and overall package volume is kind of how we'd rank this overall process. So that tends to be the way we think when we're bringing new products into the market. And then with that said, this is a sampling of new KU band amplifiers. And so our portfolio is pretty busy in KU band, and some of the amplifiers that have been in the market for 7-8 years in some cases. So what we've done with these 4 in particular is basically started off with the QPA 13, 14, the die itself, but this is the flange package version. And that's mission is wide instantaneous bandwidth for the power level. But each of these amplifiers are a derivative from the QPA 13, 14 design, and they're all designed to have wide instantaneous bandwidth. And we've also spec'd them to have an extended bandwidth from 12.75 up to, I think, 15.35, with 3 of these being surface mount packages and 1 being flange mount. But one of the overall objectives when we're doing these modern amplifiers is to just optimize them for high data throughput systems. And then at K-band, so K-band is on satellite, so satellite back to Earth transmission. And here, these are 3 of the new amplifiers that have come in the market in the last 12, 18 months or so. We've got 1 die. We've got a 40-watt die with the QPA 1721D. And then we've got 2 package devices at 20 watts with the 1725 and the 1724. And then what we've got in development that should be in market, we should get this to market in about 3 or 4 months. We've got a 10-watt QPA 1722, which will be coming into the market. And, each of these maximize instantaneous bandwidth, get as much efficiency as we can, for use on satellite. This is kind of a fun comparison, and it's taking, and it was taking a commercially available parabolic reflector type of a satellite terminal, and trying to manufacture a comparison to a low profile phased array with hundreds of elements, and to get parity, to get equal radiated power, really had to back down the power to 29 dBm on the parabolic terminal, and because the actual power amplifier that's used with the parabolic reflector, it's really easy to get 40 watts, 10 watts, 20 watts, 50 watts. And so, the ability to put tens of kilowatts in a narrow beam onto antenna is onto a satellite is quite easy with the parabolic type reflectors. But in this case, I was just kind of scaling it back to see at what power level do we get EIRP parity to an example of to one of the customers' flat panel arrays. So in this example, the flat panel array is 256 antennas. So 256 element of total beamformer ICs with 5 dBi of antenna gain, about 12 dBm power per transmitter, per PA. Then with an array gain of 48 dB, that aggregates up to 3.2 kilowatts. And then the point of comparison in the row above with parabolic, it only takes 29 dBm, so just under a watt, 800 milliwatts out of a PA with 36 dBi parabolic antenna to get the equivalent power. So it's quite easy to get tens of kilowatts with the parabolic antenna, just as a point of comparison. So on the left, those systems are architected with high power amplifiers, low noise amplifiers, and control products. And they can be fixed examples, or in this image, it has a motor on it. So this is a mechanically steered antenna. And then point of comparison is the array on the right. It's 256 elements, and so it's relatively thin, low profile, electrically steered. And that tends to be architected with beamformer ICs, or for a metamaterial type of antenna, that could be HPA LNAs. Then looking, back at the issue of high throughput systems. So, back to why do we care about high throughput systems? It's the growing need for bandwidth, higher bits per second. And so how can that be achieved, right? It can be achieved, you think of two ways. One of the ways to get higher throughput is to increase the amount of channel bandwidth that a system is using. And so that's one approach. The other approach, if you cannot increase the amount of channel bandwidth and you're fixed. So in this example, we're fixing the RF bandwidth to 30 megahertz. And in this example, we've got 3 modulation schemes listed in the table: offset QPSK, 16 QAM, and 256 QAM. And so the bit rate column shows the difference. And this is the raw signaling rate. So you go from 60 megabits per second in a 30 megahertz channel for offset QPSK, and then holding the RF bandwidth fixed, you can scale up to 240 megabits per second with 256 QAM modulation scheme. So what does that mean, for the power amplifier that's used in this transmitter? And it needs much better linearity compared to operating at offset QPSK. So we go from 25 dBc third order distortion product, figure of merit, which is much greater than the required signal to noise ratio for offset QPSK. But that's the figure of merit that's used for SATCOM uplink. But as we move to higher orders of modulation, the linear power requirements increase quite a bit. So now the amplifier is being well backed off from the saturated operating point, and the error vector magnitude, which is a metric of a measure of signal to noise ratio, starts becoming quite stringent to enable high throughput to take place. So what we're doing at Qorvo now, in addition to designing comm amplifiers for wide instantaneous bandwidth, it's also optimizing them for operation at traditional QPSK type modulation, but also for backed off modulation, for backed off operating points where high orders of modulation are required. And so, it creates more challenges, but that's what's required to remain competitive in the space and provide markets that can be used by SATCOM terminal manufacturers. And so as a wrap up, SATCOM, growing market. So for both the satellite side and the ground terminals, so that makes it quite interesting for all of us. And Qorvo offers the market, pretty large portfolio, including power amplifiers, low noise amps, and beamformer solutions. And with the growth in LEO satellite constellations and the service life of the satellites, it makes it pretty interesting for the SATCOM business for years into the future. And it just says that everyone's going to have to keep on innovating to remain competitive, to provide higher performance components and better service to the end users. Seeing the flat panel electrically steered terminals, they're pretty crucial because of tracking capabilities for the fast moving LEO satellites. So that is the wrap up. We're going to follow up with some of the contact points here at Qorvo. So I'm Paul. So I've got product line responsibilities for power amplifiers and some of the TR modules. And then James Cheng is product line manager for LNA and many of the control products. And then Ryan Jennings, director of SATCOM and systems engineering for the beamformers. And then we've got David, Malcolm, and Jeffrey as field application engineers for North America, Europe, and Asia Pacific. And with that, we can move to the Q&A portion.
Excellent, Paul, and thanks for that presentation. That was great. And it's certainly an opportunity that has the industry excited. So that was good. Thank you. Now let's take a look at audience questions, and please remember you can still submit a question in the Q&A window. Let's get started with this one. And this kind of gets to the heart of the matter right away. Are dish antenna-based systems going away?
No, they're still quite interesting, and they're inexpensive. So they're you see relatively. I mean, so the reflector itself is relatively inexpensive, and the benefits are the cost, but also high gain, right? And a simpler transceiver system, lower overall power consumption, and you can put a lot of power at a point in space with a reflector-based system.
Good, thank you. The next question, what is a BFIC?
Yeah, in this acronym-rich world that we live in, it's good to spell it out and say it, but beamformer, integrated circuit, they tend to be silicon-based. And it's a combination integrated circuit with control, power management, amplitude control, phase control, power amplification, low noise amplifiers, and then coherent combining. So on the receive side, you get coherent combining to reform the receive side beam, and on the antenna side, you've got amplitude and phase weighting to form coherent combining of the beam at a point in space. So it's a mechanism, back some time ago, we call it smart antennas, but it's effectively the ESA type of architecture allows us to do, beam forming of, low power, relatively low power amplifiers that then benefit from the array gain of hundreds of antenna elements to put a bunch of power at a point in space.
Yeah, and it's interesting that what used to be a multi-chip module hybrid assembly techniques is now an IC or a small number of ICs. This next question is more of a comment. So if perhaps you can give us your thoughts on this, that would be great. And the comment is, I think intersatellite link is very important for next generation space-based activities for the smooth operation and efficient design of RF front end in millimeter wave, mainly in K or Ka bands, is also very important. And also have to focus on low cost and simple design. And then there was a clarification that they're talking about small and microsatellites like CubeSats. So maybe if you can comment on intersatellite links and how they kind of fit into the whole puzzle.
Yeah, different methods and different frequency bands. So optical links is one of the mechanisms for connecting satellite to satellite. So optical type transceivers, which are, they can be very high data rate type of links. And then, Ka band is also targeted and used for inter-satellite links. And then, QV band is another area or another frequency band that, is or can be used for satellite-to-satellite links. And, I think we've had many inquiries into, whether it's E or W, but mid 70 gigahertz and mid 80 gigahertz type of transceiver links. Customers have expressed interest there, and that's an area that our research team has done some amplifiers there. But we've got 90 nanometer GaN that will be coming online in about 6 months or so. So we'll be building commercial products for VQ and higher bands going forward. So those should get to market 24 months in future.
Excellent. Thank you for that visibility. Your beamformer ICs are only used in the terminal design on Earth, not on satellites? Question mark.
Yeah. Presently, the beamformer ICs are used on the terminal side, and then on satellite, we're finding that the on-satellite architectures tend to be designed by the satellite manufacturers. I think one of the key differences there is the number of beams and the number of the amount of service, or the number of terminals that need to be serviced on the ground, requires quite a complex on-satellite design. So it's something that the satellite manufacturers are doing. It's their proprietary capability. So that's how it's working today.
Good, thank you. Do you have any plans for a PA with higher power than the QPA 2212 in Ka band?
Maybe. We've got a couple of initiatives taking place now, and one really is to improve linear power. So linear power is a key metric, as is efficiency. So we've got activity going on right now, GaN 1.5 for enhancement, and then 90 nanometer GaN. And so we'll see how each of those technologies play for amplifiers that are larger than so the QPA 2212 die is a 25 watt saturated power, 3-stage amplifier at Ka band. What's sort of interesting there is that for the high power SSPAs that our customers manufacture, the size of engine that they're using to build up those amplifiers, 14 watt, 20 watt type engine, and they're combining a bunch of die to build up to 200 watts or a 400 watt saturated power SSPA. At present, I think it's based on both the power, the size, the performance, the efficiency. For us, for our portfolio, an 8 watt product, a 14 watt product, those seem to be preferred for the multi-100 watt SSPAs. And then, for customers who are packaging, more of a smaller amplifier, so let's say the 25 watt or a 50 watt amplifier, that tends to move towards a package device. And so for me, looking at portfolio sales, I look at historically what we sell at 5 watts, 8 watts, 14 watts, 25 watts, and try and decide what do we do next from a portfolio standpoint. I think the sweet spot right now is at lower power, but in part, if we could build a 50 watt amplifier at higher efficiency than what we have today, I'm sure we would do it. So I think we're running into saturated power density, efficiency, linearity, for the technology. So right now we've got to push beyond where we are, but from a technology standpoint, it's getting a little challenging.
Yeah, good. Thank you.
Yeah.
And since we're talking about GaN, here's a multi-part question having to do with some of the things you just mentioned. Do GaN components work in CW or pulsed? And what is the power density? In the linear region, the efficiency is low. How do you deal with the heat? And what reliability tests are performed?
Yeah, big question. So, so GaN does operate, I'll use the term always on. So I'll use the term always on type operation for comms. And that could be always on saturated. It could be always on, say, saturated power minus 3 dB for offset QPSK, or if it's operating at some order of QAM modulation, it's going to be operating PSAT minus 5, 6, 7 dB off the saturating point. So whether saturated or backed off, it's an always on type of duty cycle. And similar with radar. So radar tends to be, pulsed applications, but we're seeing customer requirements as well as operating methods where even radar has CW operating modes. So you've got this always, and CW is a little bit ambiguous, so continuous wave, and it can be interpreted as, that's why I say always on. So radar can be always on as well as pulsed. And same thing with communications. Well, communications tends to be always on, but with linear modulation, it's going to be backed off from saturation. What we do with any amplifier, any GaN amplifier, from a reliability standpoint, through design as well as through design verification testing, is looking at junction temperature. And so at Qorvo, we tend to target junction temperature of no higher than 225 degrees Celsius at a 1E6 mean time to failure metric. And so, that's kind of a design criteria. And if we're evaluating, reliability, or actually during DVT, there's also, mechanical engineers are involved, and, we're often measuring, junction temperature with special cameras to see if model meets reality. That plays into the reliability equation. And there are some applications where the expected life cycle is not, a million hours. There are some applications where the duty cycle might be quite short. You can imagine what those are. So in those cases, the operating at a higher junction temperature might be chosen. Then in terms of competitiveness, increasing all metrics, to be competitive, continuous improvement is just needed. So getting more efficiency, getting more power density, is just part of what needs to take place in technology business, right? Performance sells.
Excellent, thank you. What types of metamaterials are used in LEO satellite antennas?
Well, outside of my area, I have done some reading in the last 6 months, which I find to be pretty fascinating. And so I kind of go to Google and I look at who has metamaterial type products. And if I know people, I'll ask some questions about it, but kind of dig into, learn, what the term is actually referring to and what they're actually doing in terms of making radiating elements and controlling radiating elements. So it is an interesting area. I speak with much expertise on it, but it is an area where I've read some and I'm curious about.
Yeah, thanks. Honest answer. Thank you. Does Qorvo perform radiation hardened qualification for these new products?
That is a good question. And Ed Peak, Ed and P-E-E-K is his last name, Peak. He is heading up Qorvo product management for space qualification. And so there is some testing that Qorvo offers. And I think if we can direct that question, or we just record the question and direct it to Ed, Ed could provide the most thorough answer to that.
Good, thank you. Do you plan to use GaN 0.1 micrometer technologies to improve performance? Is there a timetable?
We are going to be using 90 nanometer GaN. So that's what we've got. We're in the bring to market, I'll call it the qualification phase now. And so all of us on the product side, on the engineering side, on the sales side, we all want 90 nanometer GaN 2 years ago. But it is coming to production readiness. And so we're targeting start of a 90 nanometer design, April, May of next year. And yeah, we're gonna look at Ka band and above, for the application of 90 nanometer. So Ka band Satcom, QV band Satcom, E band Satcom, or E band for the 90 nanometer technology node.
Excellent. We'll look for more information on that one. What type of satellite platform, size, power, attitude control are supporting your Ka, Ku, QV products?
Wow. I don't think I can answer that question. On satellite, our K-band portfolio sells on satellite. So that's roughly the 17.3 to 21.2 gigahertz band. So we've got some older products like TJ4548-SM, both die in the package part, have been used in space for some time. And then the newer, like the QPA 1724, is used in space. Where else? I think we've got some X-band amplifiers that are also have been used in space for quite some time. And if we go up in band, the QV band amplifiers, the 37.5 to 42.5, I mean, those are targeted for on-satellite use. But that's as detailed as I could go with that question.
Good, thank you. Is Qorvo planning on integrating a Nokiwave silicon beamformer paired with compound PA LNA for better power added efficiency? And that means quite smaller DBM 3.5 PA discretes? Question mark.
Yeah. The integration in the comm space, I'm not quite sure whether things like GaAs and GaN are going to be added in a multi-chip type module format for a comm space beamformer integrated type solution. In the radar space, certainly. So in the radar space, beamformers plus GaAs and GaN for multi-chip modules, definitely from an integration standpoint. And I think in the comm space, I think we can refer this question to Ryan. And I think Ryan can provide the best answer to multi-chip, semiconductor technology integration.
Great, thank you. Which of the market segments you highlighted are using Q or V band devices?
Yeah. So right now, 37.5 to 42.5 is the band for satellite to Earth communication, and so we've got GaN on the power amplifier for satellite to Earth transmission, and I'm trying to recall whether James Chang has LNAs for the satellite for the ground station receive side. And if he doesn't have anything existing, it's roadmap or it's in development. And then on the uplink side, Earth to satellite, on the PA side, on our roadmap, we want to do 44 to 46 gig, then 47.2 to roughly 52 point something, for uplink transmission. And I think James has similar goals for the on satellite side in GaAs. So looking at GaAs LNAs to receive on satellite. So I guess wherever we're doing PAs, James is looking at doing LNAs to do the opposite side of the link.
Good, thank you. Do you have a GaN Doherty on die for 27.5 to 31 gigahertz Ka band on your technology roadmap?
We have an existing design that is a GaN Doherty, and the part number escapes me at the moment, but David Woolert is a designer, and he's published on it. So this is probably can be found in IEEE, but there is a Doherty that was designed and characterized, and we put EVBs out into the world. And it doesn't cover the full band, by the way. So it's more of a, the sweet spot is more about, I think 1 to 2 gigahertz of bandwidth. But yeah, that's an interesting amplifier. So we put EVBs out into the world at one time, 3 years ago maybe. And so with customer interest and market pull, we'd look at doing a revision to that at some time in the future, and look at offering that to the market. But it is interesting from a PAE and linearity standpoint. It is an interesting architecture because it's used a lot in mobile communications today.
Great, thank you. What type of material is used for QPA 1314 flange? Is it CPC 141?
We use the package base is all copper, so it's basically it's 100% copper, and it's one of the areas where I think it's kind of surprising to some people because of the CTE difference between the gallium nitride and copper, and so that's 10 gold of the dies, 10 gold solder to the copper base, and Qorvo has found a way to make that mechanically strong through a temperature cycle, such that when stressed to JEDEC test, the part doesn't come apart. But yeah, our lives would be easier with a material that was closer in CTE to the GaN. So I think I'm advocating that to some degree, and we played a little bit with the diamond, the silver diamond type of materials that have very nice heat transfer characteristics.
Thank you. Does the QPA 1721D use wedge bond or ball bond?
It tends to be ball bond, but for the die itself, not being a process person, I imagine either can be used during assembly, but maybe that's a point that we may want to check with Qorvo applications engineers to make sure I'm not misstating anything. But I think if so long as the bonding pad area is large enough, I think a wedge might be okay. From time to time, we'll do both. We'll do both like 1 mil gold wire bond, and we'll do ribbon bond as well. And I don't think we're doing anything different on the GaN die itself to do a wire versus a ribbon.
Okay, great, thank you. You mentioned diamond a moment ago. Here's a question about that. Do you use advanced cooling technologies, active cooling, diamonds?
Not at present in the GaN process. We're GaN on silicon carbide. We've done some work with so Qorvo does copper moly copper tabs for the die on tab products. So in those cases we're gold tin soldering gallium nitride to the copper moly copper tabs, and when we taken that further, we experimented with a number of the CVD tabs and just kind of looked at differences in thermal performance, which they're interesting. So with with customer demand, I think we would take that type of substrate forward. But then as far as other types of advanced thermal management, it is something that customers do. So the way to manage heat, they're doing it at a higher level of assembly. And yeah, but it is a very interesting area. Because, I mean, clearly performance is a function of junction temperature. You want to get that junction temperature down.
Yeah, thanks. And in the interest of time, I'd like to close the webinar here. So let me thank Paul again for the presentation and for answering questions. He took a lot. We got through a lot. And I'd also like to thank RFMW and Qorvo for sponsoring this webinar. We've captured all the questions, and if we didn't get to your question, someone from Qorvo will get back to you. And as I mentioned, the webinar has been recorded and it will be available to watch later today. You'll find it in the events section of the Microwave Journal website under the Archive Webinars and Events tab. So please feel free to watch it again or share it with any of your colleagues who may be interested. And remember, if you aren't already a subscriber to Microwave Journal, you can sign up on our website. The subscription is free to members of the industry. Now, let me close by saying thanks to everyone for joining us today. Keep an eye out for upcoming webinars and panel sessions, and I hope you all enjoy the rest of the day. Thank you.
Thank you.